Good morning, good afternoon, and good evening, all of our participants. Thank you for coming back to this fourth day of the second week of our school AstrotwinColo2021. We will continue today with the fourth lecture of Chandra X-ray data with Dr. Juan Rafael Martínez Galarza. Juan Rafael, how are you?
Good morning. I'm doing fine. Thank you. It's a rainy and gray day over here. I hope it's a bright day in Medellin and elsewhere.
Well, at least here is very sunny. Thank you very much for asking. It doesn't mean it won't rain in the afternoon, though, but at least now it's sunny. Okay, Juan, so I will put your screen up. Can you share your slides, please?
Yep.
Okay, now we are seeing your screen. Mm, Now you have presentation mode. So thank you, Juan, and the space is yours.
Thanks, Esteban. So good morning, everyone, and thanks for joining again. Today, I am going to be talking about another very important aspects of data-related astrophysics, and that has to do with time domain. What this mostly means is I'm going to be talking about variability and how overall across all wavelengths, but in particular in the X-ray domain, variability has become a very important part of what we do as astronomers and a very important part of what we discover. So we used to think of the universe as something that was static and never changing, but instead, supposing that you have enough sensitivity of in your instruments, pretty much everything is variable at different scales, in different magnitudes, and in different time scales. But the universe is a very diverse in terms of the variability properties of sources. And today I'm going to try to introduce you to time domain astrophysics, and in particular to how we do time domain astrophysics using Chandra data, and in the particular case of high energy astrophysics. So let me just start with a little summary of what happened in the last lecture. So we talked quite a bit about X-ray binaries and ULXs. These are one of the most common and frequent objects that we find in X-ray surveys, specifically when we look at galaxies. And we looked at how their spectral properties can provide insight into their physical nature. For example, in the cases of ULXs, are they intermediate mass black holes or not? And we looked at how the spectral components of these objects can give us information about the physics that happens in these objects. And we introduced the concept of maximum likelihood estimate in the context of trying to evaluate a particular model when you confront it with data. And we showed that the typical metrics you use, for example, the chi-square metric that is very commonly used when you fit models to data, actually comes from the exercise of maximizing a likelihood with some assumptions. And in a very strong assumption we made there when we use chi-square is that our errors are distributed as Gaussians. But we basically made the link between these metrics, these statistics like the chi-square statistic, and the exercise of maximizing a likelihood, maximizing the likelihood of my data given a particular model. And we also learned that when you do the full Bayesian picture and you have a posterior for your model parameters, that is very difficult. Then instead of trying to solve that posterior analytically and in an exact way, you can actually use MCMC, Monte Carlo Markov chain, to sample from that posterior. And if you do that efficiently and correctly, then your samples the histogram of your samples will resemble your posterior, and that's all the information you want in terms of the uncertainty of a particular parameter. But we also learned that when you write down the Bayes rule that links the posterior to the prior, etc., there is a normalization factor involved there that we call the evidence. And we saw the importance of the evidence when we want to compare models that attempt to fit the same data. In other words, one of the assumptions that we make when we fit a set of data with a particular model is we're kind of assuming that the model is right. But the Bayesian evidence allows us to compare different models that try to fit the same data in order to come up with an assessment on which one actually is a better explanation of the data. And we briefly introduce a method, nested sampling, that allows for efficient sampling of the posterior, and at the same time, it gives us for free the value of the Bayesian evidence, because it kind of samples by integrating the volume of probability below the posterior, and that allows us to calculate the evidence at every step of the sampling. And we used a particular code, BXA, that it's an extension of Sherpa, to fit the spectrum of an interesting source in the Virgo clusters. This was an ULX, and we did the exercise of fitting the source with two different models and look at the evidence to try to figure out which model was a better explanation. So that was last lecture, and I wanted to, just put forward the main points from that lecture. And what I'm going to talk about today, as I said, is time domain astronomy, and that's another field of data-related astronomy that is heavily, related to statistics. And we will, I will try to frame, put every variability in context and tell you why it is important. In particular, when you look at recent discoveries of very exotic phenomena, of which many more are to be discovered, we will explore scenarios of variability in X-ray sources, and I will introduce a particular type of variable source that is bright not only in X-rays but across the entire electromagnetic spectrum, which are tidal disruption events, as well as the different variability cycles of X-ray binaries. And we will learn from a statistical point of view about how we characterize variability in X-ray astronomy. Remember that in X-ray astronomy, we're counting individual photons, and in some cases, all we have is a sequence of photons. And deciding whether that sequence of photons is consistent with a variable flux is a statistically complex problem that we will try to address with a couple of techniques. And as a practical session at the end, I will show you how to search the Chandra source catalog for variable sources, learn how to bring their light curves, visualize their light curves, and explore analysis tools to obtain our own light curves if we want to actually reduce a particular source and get the light curve ourselves. So that's going to be today's lecture. And let me start with this very interesting diagram of variability in the universe. And as you can see here, the reasons why astronomical sources are variable are quite broad, and they are mainly divided into intrinsic and extrinsic situations. Intrinsic, for example, can be the pulsation modes of stars. So as you see here, stars have a number of reasons why they are variable. They can pulsate because of their own physical evolution, the evolution of the stellar system. They can also be eruptive. Sometimes there are magnetic reconnective events in young, less massive stars that produce extreme flares of radiation. But there can also be a cataclysmic event in which, for example, there's a thermonuclear reaction in the surface of a white dwarf that is accreting from a particular companion star. And then there's also things like eclipses, of course, where basically you have stars that live in pairs and they eclipse each other. So from that level down, there's a whole lot of different types of variability, and this is not even all the full picture. And you see that there's also, of course, other types of variability that have to do with extrinsic phenomena. For example, microlensing, that happens with a very massive object, passes in front of an object that is behind. And so the very massive object will act as a lens, and it will produce an increase on the brightness of this particular source. So variability is extremely, extremely diverse. And in order to characterize this properly, you certainly need to have the proper statistical tool to do it. The reason why it's so interesting to look at variability is because among the many things we have explored, there's still plenty of space to discover new types of variable sources. And because of the way we're doing astronomy these days by creating these huge surveys that basically look for variability in extended regions of the sky over extended periods of time, there is a very high probability that we will find new types of objects. For example, if you look here at this plot, this is the characteristic time scale of explosive events. Think of stellar explosions at the end of their lives, supernovas, and this is the characteristic time scale of those kind of changes in brightness. For example, when you have a supernova, you have an increase in the brightness and then a decrease, and the characteristic time scale in which that happens tell us about the actual physics that are happening behind the scenes. So here's the characteristic time scale for that, and here's the peak luminosity, how bright it gets eventually at its maximum peak. And as you can see here, there is a number of different type of supernovas. You know, we have thermonuclear supernovas, we have core collapse supernovas, in which the actual core, the very central part of the supernova, collapses due to the gravitational pull of a very massive initial star. We have certain types of transients, etc., etc. But if you look at the upper left part of this diagram, you see that it's still unexplored. And the reason why this is unexplored is probably because we haven't really yet sampled this area of this parameter space, where perhaps some of the objects that have very short time scales of the order of a day or so, but very, very bright light curves, that area we haven't yet fully explored. But these are the ones we want to find. And of course, how to find them when you are when you're taking images of the sky at a particular cadence, at a particular rate, without necessarily tracing those specific time scales for these objects, is an interesting statistical problem. So how do we find them? The reason, I mean, this is an example that these objects are actually found, and this is a relatively recent paper. Actually, I think the paper is not 2016 but 2018, but it's an interesting discovery of a pair instability supernova. And this is an object in which the initial mass of the star is so big that the collapse is massive. The collapse of the star is very massive, and as gamma rays that are produced in the interior of the star at very high pressures start colliding with atomic nuclei, they produce electron-positron pairs, and that reduces the radiation pressure of the star towards the outside. And what that turns out to, that results in a very, very quick collapse of the core. And as a result of that quick collapse, the star gets completely ripped apart. So the rebouncing of that very extreme collapse will make the star completely disappear, and not even a central object will remain in the middle. So this is kind of one of the most extreme explosions in the universe. Usually a supernova would leave something behind, a neutron star, for example. But in this case, the collapse is so massive, and the ripping apart by the collapse of the core is so intense that not even the central object will remain. And what's interesting about these objects in terms of their time domain properties is that, as you see here, and you look, this is optical magnitude, so this is not X-rays, even though we do expect wavelength emission across the whole wavelength range to be emitted. But if you look at the light curves for these objects tend to have brighter but slower light curves. So you see, these are the two examples here. And in fact, this paper reports the first discovery of an object like that even shows two peaks that are characteristics of this type of objects. So objects like pair instability supernova, objects like extreme explosions, or even things that we don't yet know about, are probably hidden in our data sets. And that is the reason why we want to be looking for these objects using statistical methods, but also methods of data mining. And therefore, we need to adopt an exploration approach to research. And this is me trying to encourage you to try to try to pose new questions instead of answer questions that are already there. We want to use the exploration approach of research in order to gain the capability to pose new questions, to formulate new hypotheses. So the only way we can do that typically is by actually opening up new observational windows that expose us to things that we have not seen before. So we don't want to deal with the known unknowns. We want to deal with the unknowns unknowns, things that we don't even know they are there, but that we want to discover. And data exploration is, of course, a very efficient way to do that. And that's particularly true, of course, in the case of astronomy, where many discoveries are actually serendipitous. I have already mentioned to you about the serendipity of the Chandra source catalog and how many sources there have not been explored. And here is a nice example of a serendipitous discovery in astronomy from 2 years ago by a team in Italy. They were looking at some region of the sky with the XMM Newton telescope. And when they were moving from one pointing of the telescope to the other, they saw this bright object that suddenly appeared in the sky. And then they tried to follow it up, and they realized that it was coming back with certain periodicity, with this kind of quasi-periodic oscillations that turned out to be the result of a supermassive black hole swallowing a star that got so close to it that it got completely disrupted, as we will see later in this lecture. And the reason why it's kind of periodic is because this star is being eaten by this very big, massive black hole in pieces, producing this very interesting light curve of X-ray emission. And this was interesting because it was a serendipitous discovery. No one was expecting to discover something like this. And however, just by pointing our telescopes up, we found that. And that's exactly the challenge of data science astronomy, is to take these huge data sets and try to come up with the objects that are most interesting to us from the scientific point of view. So why do we actually care about time domain? And in particular, why do we care about time domain things that are weird, that are anomalous? Well, the reason is obvious, because there's new physics behind these events. And I already mentioned about exotic explosions that come at the end of the evolution of a star. And we want to identify those in new and existing surveys. But there's also, for example, this very increased interest in trying to identify microlensing events, either because they represent, and I already mentioned what microlensing is. Basically, there is a massive object that is passing in front of a farther away object, and these massive objects act as the gravitational lens, and it creates this kind of increase in the flux. And if, for example, that massive object happens to have a companion, for example, a planet, you can even see that kind of signature of that planet in the light curve of that. But this is not only useful to discover planets. Microlensing events can also be used to discover black holes, supermassive or massive black holes, or intermediate mass black holes, when they pass in front of a bright object in the background, and they create these characteristic light curves. Even X-rays would get bended by this gravitational wave. So we do expect that a number of variable sources in the Chandra source catalog, for example, in a very large survey of X-ray sources, will have a signature of microlensing or gravitational lensing that will allow us to discover massive, supermassive black holes. And of course, I already mentioned yesterday a little bit about exotic objects in terms of the X-ray binaries and ULXs. And in many cases, as we will also study a little bit later in this lecture, those exotic objects can be discovered by actually looking at their variability properties and how exactly the accretion process into these objects is affecting the variability and the light curve in the X-rays of these objects. So there is plenty of motivation to do data science with time domain astronomy. There is a number of missions that are either already observing or about to start observing that are doing exactly that, scanning the sky in repeated observations to try to figure out when an object changes significantly its brightness. So for example, in the optical wavelengths, we have LSST, And LSST is an optical telescope that is being built in Chile. And in a couple of years' time, it will start looking at the entire southern sky with certain repetitions. So it will look at the entire sky, then it will come back again to the same location that it looked at first for a period of 10 years, doing that, repeated observations with different rates and different cadences in order to identify objects. And you would think, if you think the universe is static, you would think that that's a pointless activity to take the same image of the sky many times. But in this case, actually, we're trying to spot objects that brighten up so much that perhaps we didn't detect them before, and now we're detecting them because something just exploded far away in the universe. So that's from the optical point of view. There's also in optical wavelengths, but from space, and more interested in exoplanets. There's missions like the Kepler and the TESS data sets that have been observing a huge amount, hundreds of thousands of stars, to try to spot the little eclipses that arise when planets pass in front of their stars. And they've been extremely successful in the discovery not only of exoplanets and transiting exoplanets, but also of all sorts of stellar variability that we were not able to even perhaps even predict before, because the sensitivity of these instruments is so increased with respect to previous observatories, that we can actually see very detailed light curves with extremely high resolution and sensitivity that allow us to test the way in which stars behave, in which they oscillate, etc., etc., etc. But there's, again, in these data sets alone, there's plenty of discoveries to be made. And these are all public data sets that people can actually explore. And then, of course, coming closer to what is of our interest in this lecture series, there's, of course, the missions in the X-ray domains. And of course, as I mentioned before, XMM and Chandra are not all sky surveys, so they will not look at the entire sky. But once in a while, actually more often than we think, they come up with a variable source that appears that was not there before, and then they can provide information about these very interesting transient sources. But now there's also Erasita, and Erasita is a German telescope on top of a Russian-German spacecraft, which you see here. This is actually the Erasita spacecraft. Actually, it's not called the Erasita. Erasita is just this telescope here. And this is an X-ray telescope that has been looking at the entire sky in X-ray radiation, and it's starting to come up with the most complete catalog of variable X-ray sources in the sky. So Erasita, you see it here, it's a collection of actually 7 telescopes. Each of these telescopes has a similar configuration as the Chandra mirror, except that they are not nested. As you see here, there's only one tube in each of these 7 telescopes, but it also has a paraboloid shape that focuses the X-rays, and it's the main instrument on board this Russian-German spacecraft. And basically, it started to survey the entire sky. And the survey of the entire sky will last for at least 4 years. But a full scan, basically what the spacecraft does, it rotates, and as it rotates, it takes a slice of the sky, then it keeps rotating, and then it takes the next one, and then the next one, and then the next one, until it covers the entire sky. And every half a year, it goes over the entire sky once. After 4 years, there will be a number of passages of the entire sky, and that's how we're identifying sources that are variable in the X-ray sky with this very exciting mission. This observes up to 10 kilo electron volts, and it does not have quite the same resolution as Chandra has, but it has the advantage that it will look at the entire sky, and certainly, even though we cannot spatially resolve the most luminous objects, at least we will have an entire sky view of where the variable sources in X-ray astronomy live in the universe. And this is just to kind of give you an idea of the quality of data that Erasita is getting. This is the first full sky image from the first complete passage that Erasita did of the entire sky. And I'm sure here you'll see a couple of familiar objects, but in particular, Of course, there's Scorpius X1. Remember, we spoke about Scorpius X1 in the first lecture when we say it was the first extrasolar X-ray source to be discovered. And here you can clearly see how bright it is in comparison with other objects. By the way, we know that Scorpius X1 is an X-ray binary, a very luminous one. But apart from that, there's also a few more interesting objects and black holes like Cygnus X1. Cassiopeia A is, remember, also from our first lecture, we were playing with a Chandra image of this supernova remnant. Here, of course, the resolution is not nearly as close as Chandra, but you can see the supernova remnant here too. There's the Orion Nebula over here that has a lot of young stars that emit in X-rays because of accretion of the protoplanetary disk into the star and because of magnetic reconnection events, etc., etc. And here's a very, very interesting and bright source, the Crab Pulsar. The Crab Pulsar was a source that was actually the result of a huge explosion that was first observed in the 11th century by Chinese astronomers. And what remains there is a very interesting nebula and a pulsar that is rotating very, very quickly and powering extreme X-rays photons into the interstellar medium. So that's, you see the amount of information. Then we will go over the entire sky many, many times, and each time we will get a new detection, or we will notice changes in the brightness of these objects, and that's how we want to discover some of the most interesting explosive events in the universe. So moving on into X-ray variability, what is it that causes X-ray sources to vary? And of course, we've already mentioned one of the main reasons for X-ray variability, and the main reason, perhaps the most important reason for X-ray variability is that there's a lot of objects that are compact and that are accreting, and that creates an accretion disk around an object creates involves a number of processes such as dissipation of energy in the disk, because there's viscosity in the accretion disk itself. There's also, of course, thermal variability. For example, when the temperature of the disk changes, then you will notice a change in the soft component of the X-ray emissions. But there's also non-thermal processes as well, like comptonization by non-thermal electrons, and depending on whether the accretion rate increases or decreases, that rate of comptonization also changes, and then you see variability. But there's also other reasons for variability. There's, of course, eclipses. X-ray binaries can also be eclipsing. So if you have a companion object that passes in front of the black hole, then you'll have an eclipse that you can detect in X-rays. Then there's orbital modulations. Basically, that's an effect of objects orbiting each other and changing, for example, the angle at which we see a particular jet of X-ray emission, etc., etc. And then, of course, there's the explosive events. Supernova, kilonova, the merging of two neutron stars that can also produce strong flares and strong afterglows after such explosions happen, and we can detect that in X-rays as well. There are, to say it another way, there's plenty of different reasons why objects in X-ray astronomy, why sources in X-ray astronomy are variable, and they have different characteristic timescales. And that's exactly why, and you're trying to make up this variability, you're trying to characterize this variability at different timescales when all you have is a bunch of photons that you detect individually in a detector. So it's an interesting problem, but it's of extreme physical importance. Here's an example of a very extreme variable object that is variable also in particular in X-rays. This is a tidal disruption event. So remember I mentioned earlier about that serendipitous discovery of that object that had those semi-periodic oscillations. Well, that's something like this is what happened to that object. Tidal disruption events are usually found coinciding with the center of with the nuclear region of galaxies. And that's because at least what we think it happens, our model, the model of reality we've come up with to explain these events, is that there is a supermassive black hole in the center of this galaxy, and a star gets so close to it that gets the tidal force of this supermassive black hole will completely disrupt the structure of the star, pretty much turn it into spaghetti, and completely kind of break the star apart. And what happens after that ripping apart of the star is that there will be a bunch of debris, the residuals of that kind of destruction of the star, that will some of which will eventually fall back into the black hole. Some of them will escape, and they will shock the interstellar material around here, producing all sorts of radiation. But some of it will actually fall back, form an accretion disk, a massive accretion disk. And that will, of course, as usual, because of the physical processes we've been talking about in these lectures, will produce X-ray emission. And interestingly, of course, even though these objects are bright in optical wavelengths, but also in X-rays, they don't necessarily, the emission on the optical and the X-ray don't necessarily come from the same spatial scales. So for example, optical emission is more likely to come from, for example, these collisions of the material that escapes with the interstellar medium outside, whereas the X-ray emission can be the result of the accretion process very, very close to the black hole, and then it kind of samples physical scales and time scales that are different, because, by the way, you need some time for the accretion disk to form, and therefore the X-ray emission usually comes after the optical emission. But there's huge variability here. This is basically a plot for several of these tidal disruption events. By the way, we haven't detected a whole lot of these objects. We have detected perhaps 50 or so that we can confirm are tidal disruption events. In fact, these tidal disruption events were predicted long before they were observed. They were kind of a natural prediction from the fact that galaxies had supermassive black holes in their centers, and then it was only a matter of time until a star would get close enough to be completely disrupted by the supermassive black hole. And as you see here, this value here in the y-axis is basically a ratio between X-ray and optical luminosity, and you see that ratio for different tidal disruption events, it's pretty variable, which mostly implies that there's strong X-ray variability. So some of the X-ray properties of these objects is that they are typically very, very soft, and that's basically related to the emission in X-rays, mostly coming from thermal radiation from the accretion disk that has been formed around the supermassive black holes. They are very, very luminous, of course. Now we're talking, remember that we said that ULXs were, the limit for ULXs were about 10 to the 42. Well, these objects are brighter than that, and that's not quite surprising, since you have a much more massive object in the center that would be the supermassive black hole in the center of a galaxy. And they are variable in both short scales and long time scales, and the reasons for that variability is not completely understood, but certainly some of the possibilities as to what is happening is that part of it is obscuration. In other words, there's a lot of material there that is obscuring the X-rays that are being emitted in the inner parts of the accretion disk, and also delayed accretion. What I said before, there is initially not a lot of X-ray emission, but then after a while, when the material that falls back into the accretion disks starts accreting, then you see an increase in X-ray emission, and that could be, of course, another explanation for this variability in a little bit of longer timescales. So that's an extreme case, but of course, there is also variability in X-ray binaries, and X-ray binaries are variable for many different reasons. For example, they can be variable because there's X-ray pulsations that has to do with a central object, a compact object that has a magnetic field, for example, a neutron star with a magnetic field. And that magnetic field, just like it happens in the auroras here on Earth, they funnel some of the accreting material into the poles, and that creates periodic pulses in the accretion of these objects. And so you see certain periodicity in the light curves of these, in the X-ray light curves. And that periodicity is actually hard to spot. We will see at the end of the lecture a way in which you can actually measure that periodicity. But that happens only when the object has a magnetic field. In other words, when it's a neutron star. In fact, X-ray pulsations, when you have an X-ray binary and you want to figure out whether the compact object in the middle is a black hole or a neutron star, you usually look for periodic oscillations in order to rule out the black hole scenario, because there will be no magnetic field in that case. Apart from X-ray pulsations, there's also quasi-periodic oscillations that are flickering a little bit, like unstable. That's mostly noise due to instabilities in the disk. The disk is not perfect. The disk doesn't the accretion disk doesn't always have the same temperature. The accretion disk doesn't always have the same density across all the disks. So those different differences produce these flickering quasi-periodic oscillations in the light curves of X-ray binaries. And then there's also transient accretion events. So we know that there are times in the evolution of these objects, and I will touch on that in the following slide. There is times in the evolution of these objects where accretion gets increased, because, for example, there was an instability in the density of the disk, and a whole lot of material fell at once into the black hole or central star. And so that creates changes in states between low accretion and high accretion scenarios, and that usually shows up as, you know, changes in the X-ray emission in time scales, you know, of a few months, of a few years, and can last. You know, an object can go into a very high accretion stage and stay there for years before it comes down back again. By the way, ULXs, when they are accreting at super Eddington luminosity, there are stellar objects that are accreting at super Eddington luminosities. They are typically in this kind of enhanced accretion mode, ultraluminous mode, that also explains some of the variability we observe in these objects. And then, of course, there's thermonuclear explosions. You know, if the compact object, for example, is a white dwarf, and it gets a lot of material from the companion star in the form of hydrogen and helium, that will produce some thermonuclear reactions that will produce explosion in the surface of the white dwarf, and that's what we call a cataclysmic variable. But also, if the object is a neutron star, these kind of thermonuclear explosions can happen. And when that happens, what you see is something of this sort. This is basically a light curve of X-rays, and you see such kind of cataclysmic explosions that happen and produce a burst of emission and come down after some time, come down. You know, this is you know, the time scales of hours or something like that. It comes down to the original level. In fact, some investigations with the Chandra source catalog, that is a public, again, it's a public database that people can explore and try to look for these kind of things. An investigation by some astronomers of the Chandra source catalog has revealed that these kind of transients can actually be detected in sources in the Chandra source catalog, serendipitous sources that people did not look at before. And at least, you know, a dozen of these objects have this kind of profile in the light curves that, of course, provides additional evidence as to how exactly these thermonuclear explosions happen. So one of the things that I'd like you to consider after these lectures is take the Chandra source catalog, try to look for interesting signatures either of variability or of spectral properties, and check against whether or not something about that source has been published, because the large majority of these sources will be just new discoveries, and you are encouraged to try to find these kind of interesting sources in the big data set of the Chandra source catalog. So I was telling you about variability in X-ray binaries, and I hope that you've realized that X-ray binaries have been a central theme in these lectures, and I think that's because they are very interesting sources that you know, provide a nice framework to explain many of the properties of X-ray sources. And one of the interesting things about X-ray sources is that depending on where they are in a cycle of accretion, they look different both in terms of the luminosity and in terms of the spectral shape. So more or less hard photons can be emitted depending on where we are along the cycle of accretion. And that cycle of accretion usually starts in a low luminosity state where there's some, there's mostly spherical accretion into the system. There is no accretion disk. There's some material infalling from the companion star into the object. But as more material, for example, because there's an ejection of material from the companion star, that as that happens, the more and more emission due to accretion starts happening, and a more and more intense accretion event starts building up. And as that happens, then you have a jet, a relativistic jet that is formed as the result of that accretion process. And you will still be hard in your emission, but you will increase. So you will have hard emission, so a lot of hard X-ray photons, mostly from non-thermal processes, but your brightness will increase. And then as the accretion recedes, and then most of the emission starts coming from the thermal emission of the accretion disk that is now quite significant, then you start softening up, and then you become softer because you start being dominated by the thermal emission of the accretion disk here, and the jet starts to recede as accretion goes down, because this is a cycle. This is an event of accretion that there's some excess of material that is passed to the central engine, but then that will go back to kind of normal kind of situation afterwards. So as you start getting dominated by that, you become softer, and then as accretion recedes, then you will start getting also not only softer but also less bright, until you will eventually reach the point where you are again kind of in a quiescent state where accretion is minimal, but now you go back to hard emission because there's no accretion disk left for you to capture the thermal emission. So the interesting thing here is that if you're looking if you have data, for example, from the Chandra source catalog of a very luminous source, something that looks like a ULX, and you're trying to figure out whether or not your ULX is an intermediate mass black hole, or it's just a star, a normal black hole with a smaller size that is just in a very luminous state because it's going through one of these cycles of accretion, then you can do that by trying to look at the spectral shape for a particular luminosity. Because in general, for any black hole, regardless of the mass, the transition, this level here, where the star goes back to the hard state in quiescent from a softer state, that typically happens at a few percent of the Eddington luminosity. So that means, and this is the level for all of the black holes, regardless of their mass. So that means that an object that is 10 to the 39 ergs per second, so an ultraluminous object, but that happens to be well above the Eddington luminosity, will probably be up here, because for that particular object, 10 to the 39 ergs per second is basically the maximum luminosity it can reach, and it's somewhere here. And you expect, when it's coming down to a less accreting phase, you expect the spectrum to be soft. You expect the object to be located here, whereas for something like a 1,000 mass solar masses black hole, then at 10 to the 39, you're actually well below the Eddington luminosity, so you're more likely to see here. So if you look at the spectrum, during a hard phase, during the low luminosity phase, and it happens to be a hard spectrum, so you will be more confident that this is a ULX instead of an X-ray, normal X-ray binary. So looking at the hardness ratios changing over time and looking at the luminosity changing over time, which is what these authors did with this particular object, you can actually come up with an explanation and with a hypothesis about it being an intermediate mass black hole or not, just by looking at those quantities. So variability, both in luminosity and in spectral properties, is extremely important for us to characterize this kind of objects. So let's focus a little bit in short time variability. And what do I mean by short time variability? When I say short time variability in terms of Chandra observations, for example, what I mean is the variability that happens within a single observation of Chandra. So you point your telescope to your source, and your source is changing in flux as a function of time, right? And when that happens, then you can see that in the light curve, and the typical duration of that is, you know, seconds to minutes to hours, because that's the typical duration of Chandra observation. So you're seeing how more or less photons are arriving at a particular time, and you see this kind of increasing or decreasing signatures in the light curve. But this is problematic, because usually you don't have that many photons to actually have a very well-defined light curve like this one, and you only have photons arriving every few seconds, for example, and you still have to guess whether the object is variable or not. So determining whether or not an X-ray source is variable in short time scales is tricky, because basically all you have is the rate at which the photons are arriving, and you have to try to statistically tell whether that rate of photons is changing over time or not, in order to deduce what is the probability that your X-ray source is variable. But short time variability, even though it's hard to characterize, can be very interesting scientifically. And in particular, I want to point out to this very recent paper by a team here at the CFA. Some of the astronomers here spotted a Chandra source, and this is the light curve of this object, and they discovered there was a very sudden dip in its brightness that lasted for a couple of tens of kiloseconds. And the explanation they came up with, by the way, they had to test a very large number of possible explanations for it. But the ones that came up to be more likely is that what is happening, by the way, this is the location of the source in the M51 galaxy, the Whirlpool galaxy, and this is a very, very bright source. The hypothesis here is that we are in a situation in which there is a high mass X-ray binary, so a very massive star being accreted onto a very compact object. And we are so lucky that a planet is orbiting both the disk and the star, and it happens to pass right in front of the very small region that emits X-rays, which makes it detectable at such a long distance. It would be if this is confirmed, this will be the first detection of an extrasolar planet outside of our galaxy, which is quite a discovery. So, of course, again, remember we spoke about comparison of models and hypothesis testing, etc., etc. There are other reasons why this could have happened. For example, there could be some obscuring material in the disk that passes in front of it. But the modeling that the authors of this paper did was more consistent with it being a regular object than something like blobby that would pass in front of the object. So there's the importance of actually doing this kind of studies. And again, light curves like this can be hidden in the Chandra source catalog and in the Chandra archive. And all it takes is a clever student to look over the data and try to find other objects that look just like this one. So I am going to take, I think I'm going to take the full hour. I'm going to take 10 minutes to explain to you the Gregory Loretto algorithm and another diagnostic of variability, and then we'll break, and then we'll look into how to explore variable sources using the Chandra source catalog. Okay, so the Gregory Loretto algorithm is a statistical method to characterize short time scale variability. So again, as I was trying to point out to you before, it's very hard to tell when an X-ray source is variable if you have only a few counts in your observation. So for example, if this is how your observation looks like, and this is just a plot of nothing versus the arrival times of photons. So this is just the sequence of arrival times. Could you tell from just looking at this whether this source is variable or not? You probably couldn't, because it's basically what you have to tell in order to decide whether this is variable is whether the rate of arrival is constant or not, or if this is more this is more better explained with a Poisson process of something that has no variability, right? In fact, the first idea that you could come up with is, okay, let's bin these events into bins of equal size in time and see whether we see variability. So your binning in this case would be kind of similar to constructing the light curve. You're seeing at how many photons arrived in this time versus how many photons arrived in this time, etc., etc. The thing is that, of course, your binning decision will impact your judgment as to whether this thing is variable or not. So, for example, if you do a bin size every 2.5 hours, this is what you see. And then you can say, well, is this still consistent with variability, or this is more like a more or less flat light curve, which has large error bars here. But if you bin in every 15 minutes, then you see something like this, that you could say, okay, there's clear flares coming up from this object. So what is really the answer here? So the Gregory Loretto algorithm is a diagnostic to try to statistically figure out how this happens, right? So basically the way we do that is by calculating the odd ratios, right? Basically in the press, if you compare the odds of a particular binning to come up by chance. So if you assume a null hypothesis in which there's no variability, and you try to estimate what are the odds of obtaining exactly this binning when you bin every 2.5 hours, and it turns out that the probability of getting this by chance is very high, then you can conclude that variability is unlikely, because it's very probable to actually get this distribution just by chance. Whereas if it's not, if it's very hard, the probability of getting this particular number of counts in each of these bins is very low, as compared to a model that, when you confronted with the null hypothesis of no variability, then that means that you probably have variability. But then you have to do that for every single bin size, because you don't know in principle which bin size will better characterize the variability. So what you do is you estimate that odds ratio what are the odds of getting this by chance versus what are the odds of getting this by chance, and you do that for all different sizes of the bins up to a maximum value, and then you compare, you kind of produce a weighted average of those histograms weighted by their odds ratio, and that will give you a light curve, and that final light curve will tell you whether there's actually variability. And of course, the odds ratios themselves will tell you whether the object is likely to be variable or not. So the way you do that is you have a number of events, right? And you bin them in m bins that are equally spaced in time. So m can run from, for example, 2 to a maximum number of m. So you can start with only 2 bins and you can go to, 30 bins, right? And for each value of m, so for each different binning, you try to estimate what's the likelihood of obtaining the distribution of events in those bins exactly. And how you do that? Well, there is this term called the multiplicity that will tell you out of all the total, out of all the m to the n ways in which you can bin n events in m bins. So this is basically the total number of ways in which you can bin n events in m bins by placing them differently, but binning them in a fixed number of bins. Then the multiplicity of this observed distribution will be like that. So out of all those possibilities, in how many arrangements do you actually get this specific distribution? So the ratio of those two, the ratio of how often you get the exact observed distribution divided by the total number of ways in which you can do it, will give you the odds. It will give you the probability, actually, that this distribution came up by chance if you are assuming no variability. And so the odds, if the number of ways in which the observed distribution could have arisen by chance is large, then the probability of it being variable is small. If there are many possible, if coming up by chance with such distribution is very common and very likely, then you're unlikely to be variable. So that's how the Gregory Loretto algorithm works, by estimating the rates of different binings and looking at the odds that that particular distribution, these particular distributions came by chance, if you assume no variability, that's how we estimate probabilities of variability in the short time scale in the Chandra source catalog. And that's actually, if you look at the Chandra source catalog, you will find variability probabilities, and the lie curves from the Chandra source catalog will actually come from this estimation of the Gregory Loretto algorithm. So this is how they are compiled. Okay. Now let's think about long-term variability instead. So now we're not interested in the variability of a single observation, but what now we're going to try to determine if something is changing in brightness over longer period of times. And the way we do that is by looking at the different posterior distributions for the fluxes. This is exactly what we did in lecture 2 in the practical exercises where we use PyMC3 to try to determine the fluxes. And if you remember, what we did is we had a source that had been observed several times. And how do we determine if that source is variable? Well, it's easy. We look at how the different probability distribution functions are for the fluxes, in the different observations. So basically, each of these kind of curves here is a probability density function for the flux of the same source, but in different observations. And we see that this is how distribute. Is this consistent with variability or not? You could in principle say yes, because all of these guys were here, and in this particular observation, the source came up as being slightly brighter. So if you can assess that this difference in brightness with respect to the bulk of the other objects is significant, then you can conclude that the object is variable. And the way in which you determine whether that change is significant is by doing a ratio of likelihoods. So that's all you do. So basically, you have a model, right? You have a model, a maximum likelihood for a model in which you fit all of these with a single flux. So you're going to assume a model, and this is what we did in the practical exercise. We assume that there's only one flux and that these guys are samples from that single flux, and that will give you the likelihood of these objects being generated and being drawn from a single flux, right? And then you do another model and you calculate, you maximize the likelihood of each of them having a different flux. So you feed a flux for this one, you feed a flux for this one, you feed a flux for this one, and then that will give you a likelihood. So all you need to do next is decide which of those two likelihoods is larger. And the way to do that is you do a ratio of the likelihoods, right? And a ratio of the likelihoods is the same as a differences of the logarithm of the likelihoods. And that's why you get this value that you get by making the difference between the model, the likelihood of the model that assumes a single rate versus the likelihood minus the likelihood of the model that assumes more than one rate. And that will give you the likelihood, the ratio of likelihoods of no variability versus variability, right? And it turns out that this quantity should distribute as a chi-square distribution. So we can use the same diagnostic that we spoke about in an earlier lecture to decide whether the source is variable, right? So if you assume no variability, right, this is the distribution of chi-square values you should get. This comes from basically the distribution of this likelihood ratio will have this shape. And that is when you assume no variability. So if you if you do the experiment and get an chi-square value that happens to be here, then you can conclude that there's no variability because it's very likely to get that value when there's no variability. But if instead you get it around here, then you can reject the null hypothesis that there's no variability, and that will give you basically a hint that this object is very variable. And by counting the amount of probability that remains at probabilities larger than that one, you can come up with a probability of variability. So that is how you characterize long-term variability when you have this kind of complicated posterior probability distributions for the fluxes. And this is how you do it for short-term variability. So I'm gonna take a break now. It's exactly 1 hour now. It's 11 a.m. We're gonna break for 10 minutes. And then I'm gonna show you a little bit as to how to select particular sources that are variable, how to use the tools, CSC View, that is our application for exploring the Chandra source catalog, to download those light curves, visualize those light curves. And then if we have the time at the end, I will show you a small tutorial as to how to extract your own light curves from Chandra data. So with that, I'd like to take a break. I don't know if there are any questions that I can answer at this point or whatever.
Okay, thank you, Juan Rafael. Yes, you have one question here in the chat. Is how common could it be that the GL algorithm returns a most likely light curve that is way different from the real one?
Thanks, Joshua. That's a good question. There is no final answer as to which algorithm better characterizes a particular variability profile of an X-ray source. I like the Gregory Loretto algorithm because it does this very interesting, almost kind of Bayesian prior-based approach where it weights the different binnings. But it is actually likely. I mean, the answer to your question depends on exactly what you mean by the real one. Again, all we can get here is an estimate, a model of nature, but it certainly tends to fail more when you have, of course, low counts. So the Gregory Loretto algorithm, for example, if you do it for only for a source that has only a few counts, it will try to smooth those individual photons arrivals as peaks, and you will see something that looks like a light curve with several flares, but that's not what's actually happening. What's happening is that the algorithm is assigning those kind of smooth peaks to individual photon arrivals at particular times. So this works better when you have, say, more than 50 counts or something in your count. But in general, for those cases with higher number of counts, is pretty robust in the sense that it gives you a quite precise shape of the light curve in terms of the arrival rates. So you just have to be careful with low counts, but in general, the GL algorithm works very nicely.
Okay, thank you very much, Juan. So Juan Rafael and I will turn off our cameras and microphones for 10 minutes, and we will be back at 11:13 Colombian time. See you in a minute.
See you in 10 minutes.
Okay, we are back after our 10 minutes break. Thank you very much, Juan. Let's then continue with the exercises of today. You're sharing your screen. Yeah. Do you have your... Okay, there you go.
Okay, you see my screen, right?
Yes, correct.
Okay. Give me a sec. All right. So I am going to start right here. Okay, so what we're gonna do is we're gonna do a little exercise of exploration of the Chandra source catalog for variability, and I think you should have installed in your machines the CSC View software that is something like this. The CSC View application is what we use to explore the Chandra source catalog and do quick queries and retrieve data, both tabulated data and data products. I did show you yesterday how to do that with Jupyter Notebook, and that can be a very interesting way if you want to do certain types of things like getting an output and putting it into a machine learning algorithms or things like that. But sometimes you want to do some visualization, quick visualization of data, etc., etc. So you can do that instead using CSV View in combination with Topcat. Which is another tool for visualization of data. So what I'm going to do is I'm going to, because we're talking about variability, I am going to remind you of these really nice plots that we did yesterday. And remember, this is just from a collection of X-ray sources in the vicinity of M33. And it's got a whole bunch of detections here in the Chandra source catalog. And all we did was we collected all of those detections and we kind of plotted their variability properties here. So just for you to remember, these here are the hardness ratios. So this is going to tell you about differences in the spectral shape of sources. So things that have higher hardness ratios will be harder, which means most of the photons will be hard photons, whereas objects that are down here are objects that will be soft. In other words, most of the emission will be by soft photons. So, and they are color coded in each of these plots by the two types of variability that I just described in my lecture. So this is the probability. The colors here represent the probability that the object has been that the object is variable in the short time scales. So these probabilities come from the Gregory Loretto algorithms that tries to evaluate the probability of variability from the arrival times of individual photons in short time scales. Whereas here, we're color coding them by the variability probability in longer time scales. This comes instead by comparing the fluxes of each of these sources in different observations, because sources in the Chandra source catalog, many of them have been observed more than once. And here what we have is a comparison of the fluxes for each of them in the different observations with this two likelihood methods and the likelihood ratio method to try to determine if a source is changing significantly in flux over longer periods of time, right? So this is basically where we left it. And what I want to try to do now is I'm going to try to show you how to do a similar query using CSV View, right? And then I'm going to show you how you can maybe select one of these points of interest here, and perhaps come up with a like curve for that object and see if you can visualize it. Okay, so let's try that. So let's start with CSV View here, and usually when you start CSV View, this is what you see. This is basically the starting page for CSV View, and it will have the different releases of the catalog. We are currently in a version 2.0.1. So in order to start your search, you will select that particular release of the catalog and then do a search. And next you will get this kind of window, and then there's a number of different things in this window. So here the most important one is probably the result set. So here you will have the the list of all the properties that you want to list in your table. So the catalog has many properties, but you typically just want to select some of them. And here, as you can see, there is basically fluxes and variability probabilities and the hardness ratios for the sources. So these are all the sources that I will sample. Typically, you can start from an empty form, and then there is some standard queries on that part. So if you just want a basic summary of your source properties, then you could take this master source summary and actually drag it here, and then it will show you the actual properties that you will be sampling if you do this. And here instead, in source properties, is the full list of sources. So you have at the master source level, you have all the sources that are computed as part of the Chandra source catalog, the significance, the aperture photometry, namely the fluxes, the spectral hardness ratios, the parameters of the spectral fits, etc., etc. So if you wanted to do a plot like the one we have in the notebook, for example, for that region. So remember, we were querying M33, and we were doing a search of about 1 arcsecond around, 1 degree around M33. So that's what I'm going to do. And I'm going to try to get all the sources, right? I'm going to get these properties. I think one important one to have here that is currently not here is the variability probability in this property that we plotted here. We want to have it because it's the one we want to plot against. So the variability in short time scale. So that's called var intraprop. Intra refers to internal to the observation because it's variability within a single observation. And so you can look for it here, right? And here you have your var intraprop B, and you want to add it here because you currently don't have it. So you want to be able to include that one. So you can drag it here, and now you have it, right? And now, because we're interested only in sources that are within 1 degree of M33, then we're gonna say, we're gonna do a cone search, right? Which the same thing that we did in the Jupyter notebook. And I'm gonna say, okay, I'm gonna go for M33, right? And I'm going to do a search of 1 degree. So when you do that, you can do the search, and what you should get is a table, right, that contains these properties that are listed here for all the sources within 1 degree of M33. And so let's do the search by clicking search here. And after a little while, my sources should appear here on my CSE2 view, that shows you the results. You know, depending on the internet connection, it can take a little bit of time, but eventually the sources will show up here. There they are. So there's 750 sources. And here you see the identification of each of the sources, right ascension, declination, etc., etc. How significant the detection is, etc., etc. So now the cool thing is that you can directly translate the output from CSE view to a visualization software like TopCat. So this is TopCat here. I'm gonna just get rid of some windows. So this is the main window of TopCat here on the upper right. And the cool thing is TopCat, for those of you who don't know it, is software that deals with large tables, and it allows you to easily plot, easily display all those different tables. And I find it very, very, very useful for this kind of data analysis where you have lots and lots of columns and you want to try to plot different relations between those columns, etc., etc. So the cool thing is that you can always from CSE view, you can use the send command and send the table to TopCat. And when you do that, this table that you just queried will be moved into your CSE view session, and you will have a table here. And in this case, it's called CSE results 3. I had moved it there before, so that's why it's already there. And you can always look at that table with this command here that looks like a table. You'll get the list of all of the observation, all of the Xray sources within within the 1 degree of M33. So now what I'm going to do is I'm going to just do the plot. And I actually already had the plots there, but I kind of made them smaller here. Where did the other plot go? Let me do this. One is here. And the other one, I don't know where it went, but we'll find it later. But basically, what you need to do here is, if you want to, let's just do the plot again. You're gonna start from your table here, and here this empty kind of white square will help you plot things. And all you have to do is click on it, and then you get a plot window. And now here's the table that you're currently looking at. And now what you want to say is, if you remember the plot, it was the hardness ratio, sorry, the hardness ratio in the HM versus the hardness ratio in MS. So that's the quantities that you will select here to play, HM versus MS, right? So here's your plot again, but now you're going to use this option here that allows you to color code, and you're gonna say you're gonna use the aux option here. That basically means that there will be an auxiliary axis, and that axis can be whatever you want of the other properties. So I'm gonna select it to be the variability probability that I dragged in before, but intraprop B. There we go. And I am actually going to make these dots a little bit larger, and this is my variability scale, but I don't like this color, so I'm gonna go here and I'm gonna do this color instead, and I'm gonna flip it so that it looks more like the one we had in CSU in the Jupyter notebook. So what this tells you is the same information as before, but now let's say you're interested in getting a Likert from one of these objects using CSC view. So I'll show you how to do that next. So in theory, you would want, probably you want to get a Likert that is reliable. So you want something that has a high significance. So let's make another plot here with the same quantities as I have here. So I'm going to use exactly the same values in the X and Y axis, and I'm going to plot them here, just copying and pasting here, right? And now you have your same thing, but instead now I'm going to do my color coding not by variability probability, but by significance. So I want to see which of these sources actually are very, very bright, because they really raise up from the level of the noise. And in order to improve this a little bit, I am going to do this in a logarithmic scale for the color bar. And again, I am going to change the size of the dots to make them more visible here, and I am going to switch to a different color here, maybe the same one as before. That was not this one. It was blue, red, blue, and I'm gonna flip it, right? So what you have here is two plots of the same data points. In this case, in this plot here, they are color coded by variability. So the redder ones are the ones that are more likely to be variable in the reds. More variable in the short time scales. And instead here, they are color coded by significance. So the redder points are the ones that are brighter and more significant over the noise level of the X-ray observation. So if you look, there's this one here that seems quite significant. I'm going to pick it. And when you pick it here, you also pick it here, and you also pick it in the table. So it corresponds to this source. And now that we pick it, we can see that that source is not only significance, but also it seems to have a pretty high probability of variability in short time scale. So this is potentially an interesting object. It's significant. It's got high variability, and so I can probably have a Likert for that object. So let's try to see that. And since I can also get that object, so you see, as I change from point to point, you also change in the table. So since what I want is this object here, then I pick that object, and now I have the name for it. So let's try to see how the Likert for this object looks like, right? So let's go back to CSV view, right? And now I'm going to do a query, right? But I'm not going to do the consearch anymore. I'm only interested in one single object now. So I'm just gonna drag the name here, the name property, to the search criterion, and I'm gonna say, just give me sources whose name is the name I just picked from the other table. So I am going to just get the properties for this particular object, okay? And now I do my search, and here's my object. And of course, now it's a table, but it only has one row because I only have one object. But what's interesting is that in CSV view, you can also get all the products. So if you were interested in the spectrum of this object, remember we fitted a spectrum. We got the PHA file, the ARF, and the RMF files, and we use that to fit the spectrum. Okay, we can get those, but you can also get the light curve. So I am going to get the light curve of this object. So let's see what happens. I'm going to select my object. I'm going to say, okay, I want the light curve for this object, and then I'm going to do a search. And as you can see here, 4 files come back. The reason why we have four files back is because this object happens to have been observed 4 times during the Chandra lifetime. So Chandra has looked at this object 4 times during its 20-year mission, and each of these files correspond to a single observation. So because we know that the object is variable, it seems to be highly variable in at least one of the as a master source. That means that it should be variable in at least one of the observations. So let's try to have a look at the light curve and see what the light curves look like. And again, this light curve was produced using the Gregory Loretto algorithm. So I was trying to weight the odds that the object is variable based in all possible meanings of the arrival times of the electrons. So let's start with, say, this observation. And again, this is a fits file that contains the light curve. It will be basically a count rate versus time. You can also send that one to TopCat. I am doing that right now. And I just did it with the send button. I click on send, and then I select TopCat. And here now appears in TopCat my data set for that light curve in particular. If I just do a click here, then you will see that for this particular light curve, there is a big jump in flux. You don't see it necessarily clearly here, but if you go to I think form and then add a line, then you will see that in fact, you know, in this observation, most likely we didn't have a lot of counts. So this light curve doesn't have a lot of points itself, but it does show a significant increase in the flux for this source. So there is there is variability for this object here, and you can of course see if the behavior is similar for the other light curves. So you can send this one also to TopCat, and after a couple of seconds, it will appear here as a new light curve that you can again plot, and then you have a similar behavior, etc., etc. But not all light curves will look like this. So in this case, we did the exercise of actually selecting a particular source and try to get the light curve. But other objects have light curves that look more like this. For example, this is another object in this region, and this one that has a significant amount of counts shows significant flaring activity. And this one here is probably real because this object it's an Xray binary that is undergoing some transitions and some explosive events, and you see, if you actually do the adding the point here, you will be able to see those flares that happen for this light curve. So this is how you get light curves from the Chandra source catalog using CSV view of particular objects of interest. And those objects of interest can be selected based on their variability properties or their spectral properties. You could be, for example, interested in an object that instead of being very variable is very soft. So here's a very soft object that is also very variable, probably not very significant. If we look at the other plots, it's got a low significance, but still interesting to look at. This is more significant, also soft, but not so variable. So you can explore all these possibilities for different sources and actually get the data products from the Chandra source catalog for each of them. So now let me show you a little bit how you put all these sources in context. So in the notebook, I had shown you an image from the ESA Sky platform that allows you to visualize these X-ray sources and put them a little bit in context. So you see here. So let me show you a little bit how to do that. So in theory, all you have to do is go to ESA Sky. So you can actually go Google it, ESA Sky, right? And the first result you get is actually the application. And Sky is a very, very nice application that allows you to explore multi-wavelength data sets and actually plot a lot of catalog information, both in the X-ray and optical, etc., etc. So let's go to our region of interest. So that's Galaxy M33. And if I just type the name of the object of interest here, it will actually take me to M33. So here's M33, and here with this little button here, I can see different views. In this particular case, I am looking at the infrared with the WISE mission that was an infrared telescope. But what if I just want to add a view in the optical wavelengths? So here's M33 in optical wavelengths. And you can actually drag this thing to move from optical to infrared. You see, for example, how these star-forming regions suddenly brighten up in the infrared, because these are where stars are being formed. And of course, you can also add X-ray data. And I'm going to say X-rays, not from Newton, but from Chandra. And this is what you get. So you see that, of course, in this case, you don't see all the spiral structure, because all what you're seeing here is actually only the very most energetic objects that happen to take place in this galaxy. So any guess for what the central object could be? Well, that's not too hard. That's probably the supermassive black hole in the center of this galaxy. You see that as I move from the optical to the infrared into the X-rays, you see that that point here coincides with the X-ray point. Of course, there are other points here that are probably X-ray binaries. These are all probably all the sources that Chandra detected. So can I get the Chandra sources and try to put them in context here? Yes, I can. So all I have to do, all I'm going to do is I'm going to visualize exactly the same sources that I had in these plots, right? But I'm going to actually put them in the context of what's being observed in that region of the sky. And so here there's a button that allows you to explore catalogs. And if you click on that button that looks like a map of the world, you will have all the catalogs that have elements in this particular region of the sky. So including the Chandra source catalog, of course. So I'm going to just click on Chandra source catalog. And what will appear there is a bunch of squares that are the Chandra sources that have been detected in the region of M31. And also a table with some basic properties from the Chandra source catalog. Not all of the properties, but some of the columns that we have provided to the ESA Sky team to actually display in this platform. So that's interesting. We have all these nice sources, and some of them are very bright. Some of them you can almost not tell. You can zoom in and look at some of them a little bit closer to actually convince yourself that there's actually a source there, and a source here, and a source here. But this is actually all the sources in this region that were part of the Chandra source catalog. And you can, of course, see what they correspond to. And you will see that some of them live in the bright star-forming region. So they are likely to be young stars that are emitting in the T Tauri phase, that are emitting as material is being accreted from the protoplanetary disk into the surface of the star. Some of them are very bright and displaced from the center of the galaxy. So, for example, if you look at this object, let's zoom in a little bit. This object here, this one, if you see, that doesn't really fall in any star-forming regions. It doesn't really fall in anything particularly interesting. This is probably just a star in this galaxy that happens to be orbiting a black hole and accreting and getting this very extreme X-ray source. So one of those famous X-ray binaries that we've been talking about so much in these lectures. So this is another way in which you guys can explore the Chandra source catalog by doing this visualization in ESA Sky. And I already show you how to bring down the data products using either a notebook, a Jupyter notebook, or the application CSV. One other thing that you can do here that I think it's important for research is you can also come up with publications. So if you click this button here that looks like a hat, like a graduation hat, you get a dot for every paper that's been, or every object that has papers about it in the literature. So this is extremely useful. It can also get extremely crowded. But let's look, for example, at that object that I was telling you about that looks like maybe an Xray binary. Let's see what people have published about it. There's 21 publications about this object. And, you know, ultra luminous X-ray source. So this is actually a ULX, so probably a binary, but very, very bright. And here are all the papers that have been published about that source. So you can explore, catalog sources. And by the way, if you want to do serendipitous discoveries, you probably only need to find your source of interest and then use this nice tool here to figure out whether anything has been published about it. Okay. All right, so that's about exploring the catalog with a different number of tools. The last thing I wanted to show you today before we close is there is a number of interesting tutorials in the Chandra website that show you a number of things and tutorials of how to do things. I was telling you about the Gregory Loretto algorithm. There is a Chow tool that actually computes the Gregory Loretto light curve for a source if the input is just the event file. So all you need is the event file with the arrival times, and it will create the light curve, and it will also give you probabilities of variability. So that's the tool that we actually created for the catalog that we have turned into a standalone tool that you can use to estimate your own variabilities and your own probabilities. But what I wanted to show you was how to do basic light curve extraction. And there is a tutorial called Basic Light Curves. And if you just type Chow Basic Light Curves, this will come up, but I'm happy to provide you with the link as well. And this is a nice tutorial that you can follow to do light curve extraction from Chow directly using your Chow installation. So this doesn't use the Gregory Loretto algorithm. This just takes the event files and tries to find some kind of optimal binning to try to display your light curve. And the way it works is very easily. I mean, this is basically the workflow. You first download your event file of interest. So I am going to download 2 observations from the Chandra source catalog using my Chow tool, download Chandra ops ID. This file you can probably have, because I have passed that to Esteban in case you want to play with it. But what this is doing is it's downloading the event files for these 2 observations, okay? And now we're going to take 953, which is an ACES observation. Remember, ACES is one of the 2 cameras that Chandra has. And I am going to try to extract the light curve for sources here. So the way you do that is you actually load your event file in DS9, right? And in DS9, basically DS9, you can probably have it installed. It looks like this. If you have Chow installed, you just type DS9 in your terminal, and then you get this window where you can load your different images. And all you have to do is create regions around those objects to try to estimate the light curve. So basically, the way to do that is you select a region that contains your source, select a region that contains your other source, and then you select also a background region. So this is basic photometry. Of course, you need the source region, and then you need a background region, right? And usually that's very easy to do in CSCV. Sorry, in DS9. If I was gonna do that for this particular object, I would just select region here, and then click close to the region. Then I'll have a circular region. You can also change it to elliptical if you want to, but then you can have a region that contains your photons, and then you can create another region over here that you want to say is your background region. Usually you make it much larger, but for the moment, let's say this is going to be your background region. And then you can save those regions, right? You can save those regions within DS9. If you say region, save regions, you can save them as files. That's exactly what you do here. You save your regions as files in DS9, and then you do a number of steps The tool that we will use for extraction of the light curve is actually DM extract. This is a Chow tool that will extract the input events and turn them into a binning version of them that you can use to construct the light curve. And the way in which you do that is you just set in DM extract, you set your input file, that's just your so this is all done from the terminal. So if you have Chow installed, all you have to do is set these parameters before you actually run the M extract. So the M extract, you will tell what the input file will be. You have to specify which CCD of the array. Remember that the focal plane of Chandra has more than one CCD. You have to specify where it falls in the sky, in which CCD the source falls. You select the region, so you saved your region, right? And you're saying, okay, the source for which I want to extract my light curve is the one contained in this region. And then you will also you can also already select a binning in time here, basically every 2000 counts. So that's what you're doing, selecting a binning for the time of the arrival photons. And then the light curve, the out file will be this one. That means basically that's where your light curve will be saved. This is just your background. So you're gonna say my background region is the same event file, but now my region is the other region that I saved as background region, and you have to specify that here. Here, this option just basically is telling DM extract that what you're interested on doing is doing a light curve when it does the extraction, and then you just run DM extracts. And once you do that, you will get this file that will contain your light curve. If you then want to visualize, then you can load this light curve either in Topcat or Python, or even using any other utility you use to visualize FITS files, and you can actually plot the light curve. And in this case, we do that with some of the tools from Chow that allows, but this is done from Python, that allows to plot the light curve, the error bars, and labels, of course, the axis with whatever they contain. So this is going to be our light curve here, you see, and this is an interesting one. So this was the light curve extracted from one of the two sources that were here. I think it's source 2. And what you see there is an interesting pattern in the variability of the source, where you see that the error bars are small enough that they basically make these variations credible, because the error bars are much smaller than the actual scale of this variability. So in this way, you can extract your own light curves using a very simple recipe using Chow, and but you can also trust the algorithms that we have applied to the Chandra source catalog and actually get the light curves already processed from the Chandra source catalog directly using the CSC View application or your Jupyter notebook. Okay, I think that's what I had for today. I ended up a little bit earlier than usual, but that's fine. Maybe that will leave some space for questions. Tomorrow will be the last session of the school, and it will be a short session. I want to introduce you to some basic concepts of machine learning. So I've done my best to try to give you some basic notions of probability, how probability is applied to analysis of data sets, in the particular case of X-rays. And tomorrow, I want to give you some notions on how that probability can be applied to define very simple machine learning models that you can then apply to large data sets. And in particular, I'll be focusing on things like classification of objects based on properties, but it will be a relatively short session, maybe 40 minutes or so tomorrow at 10, and that will conclude the school. So I hope today's session was useful, and please do let me know if you have any questions. And I guess Esteban left, and he was assuming that I was gonna finish later, but anyway, I don't know if you guys are able to provide any questions, so I'm just gonna wait for Esteban to sit in the control room and tell me whether there's any questions. Oh, there he is. Oh, there's Herman. Hey, Herman.
Sorry, we have a bit of a delay here due to the projection in the room. So give me a second while I check the transmission. Okay, I don't think we have any new questions.
Okay.
But yeah, no, I don't think we do. Let me check. Nope. Nope. We don't have any.
Okay, so we'll meet again tomorrow for the last session on machine learning methods. It will be a relatively short session, and with that, we will conclude the school.
Thank you, Juan Rafael, and I'll see you tomorrow then.
Yes, and please, if students have questions and don't dare to ask them here, just tell them to just drop me an email, and I'm happy to help them with any technical issues they have with the tutorials or with any questions about the topics we've been covering.
Perfect. Just one last thing. Tomorrow's session will be completely online, just in case anyone has a plan to come here physically. Okay.
Okay.
Permission.
All right. Well, thanks.